As I do every day, could I ask some of the students to please show themselves, just to interact a bit? That's okay.
Candidates, please switch on your cameras and interact with Professor John. Yes, anyone from the audience? Yes, Jagriti is here.
Okay. Hello. I don't know why the others are so shy. It's a bit strange to me, but I'm being completely honest, but I cannot change it. So let's continue like this. All right. So yesterday we discussed a number of results from random matrix theory. One question on the chat was, how random matrix theory is useful in applications. So, as I have answered on the task, on the chat, sorry, the RMT is used in literally every field you can think of modern data processing field. I mean, in machine learning, in inference, in neuroscience, in finance, in any place where you encounter large matrices, RMT is used. So this is a very important tool. It's a bit like asking how is the Fourier transform used in the real world. It's used everywhere. It's a very generic set of tools. Okay, so yesterday we spent quite some time discussing this BBP transition, which is this phenomenology where if you look at a spike model, which again is a GOE matrix perturbed by a rank 1 matrix, and there is some tau here that plays the role of a signal-to-noise ratio that appears. Remember that this is the mapping to the old notations. Okay, we just rescaled everything by square root n. The question is, how does this rank 1 matrix changes this GOE matrix? So can we see from D that there was or not a rank 1 matrix hidden in it, or is it pure noise? Is it only this H component? Okay, so this result gave the answer. This result told us that if tau, the signal-to-noise ratio, is less than 1, which is the BBP transition in this problem, then the top eigenvalue of the data of D converges to the endpoint of the spectrum of the noise. So it's you only see a semicircle. Okay, so you cannot tell that there's data that there's a signal component in the data by just looking at its spectrum. Okay, that's not enough because you would only see the spectrum of pure noise. On the contrary, if the SNR is greater than the BBP transition, you see an outlier eigenvalue that escapes at this location. Okay, I'm actually going to take the time to show you how to derive it, as well as the BBP transition. And so from that point on, from that SNR and higher values, you can detect the presence of information, of structured information hidden in the noise. Okay, and the second part of the result is the eigenvector overlap. So it tells you that V1, which is the eigenvector associated with this largest eigenvalue, can be thought as an estimator for this unknown vector to recover U, and so you can project this estimator onto the unknown vector U, This is the inner product. And the square of it, so why do we take a square? Because, of course, an eigenvector, like we're not measured, like U is measured, but up to a global sign. So, right, so you should keep this thing in mind, that if I take U or plus or minus U and I plug it there, the D will not be changed. It means that because I'm measuring a quadratic function of a vector, I'm losing information about the potentially global sign, okay? So the best I can do is to reconstruct plus or minus U. I can never be sure that I've reconstructed U itself. Maybe I reconstructed the global opposite, okay? So that's why we're looking at the inner product between V and U and then take an absolute value or square. And so this is a performance metric. It tells us how well is aligned our estimator with the truth. It's given by 1 minus 1 over the SNR squared, okay? And so therefore you see that when tau goes to infinity, when the SNR becomes very large and the data should contain only information, and indeed even this very simple estimator aligns completely with the truth, and the overlap tends to 1. So it means you reconstruct perfectly the vector as it should when the SNR goes to infinity, okay? Perfect. So then what we have done is also to derive the the semicircle law based on computing the Stieltjes transform by the cavity method, the Stieltjes transform of the GOE ensemble, and then using the Stieltjes inversion formula, we got back the semicircle law. Okay. So what I want to do now is to derive, to give you some ideas on how to derive this result. It's not complicated, so it's interesting to take a look, and it will give you some important basic tools from RMT. So personally, I think that if one does no derivation at all, shows no single proofs in a theoretical course like this, it doesn't make so much sense either. So as I said at the beginning, the most important for me is that you understand the concepts, what we're talking about, but having some methods, some proofs techniques is also important. It's at some point you need to do it also to understand. Okay, so what we want to identify is what is the critical value of the SNR beyond which an outlier escapes the semicircle law. When is the perturbation, the rank 1 perturbation of this GOE strong enough such that it will escape the bulk of eigenvalue due to the semicircle law? Okay. So to prove this, we're going to use a very simple formula, which is very important to know, at least that it exists. It's called the Sherman-Morrison formula. It's a generic results from linear algebra, like the Schur complement formula gave us a recipe to take inverses of block matrices. Okay. The Sherman-Morrison formula is a formula to get an inverse again, but of a matrix perturbed by a rank 1 matrix. Okay, so the point is the following: if you have a matrix A that is invertible and you perturb it by a rank 1 matrix, and assume that you already know the inverse of A. Okay, you already took the time and computational effort, you've done and now you're just adding a rank 1 perturbation. So at the level of matrix, adding a rank 1 matrix is really like a perturbation. It's just a matrix with one non-zero eigenvalue. So it should not modify too much the original matrix. And so somehow you should be able to exploit your knowledge of the inverse of A that you already have in order to get the inverse of the perturbed matrix faster. And this is the case indeed, and Sherman-Morrison tells you how to do that. So X and Y here are just vectors. such that so capital letters are capital bold are matrices, bold small letters are vectors. So this is a rank 1 matrix. Okay, it's a column times it's a column times a row. So the inverse of such a rank 1 perturbation is equal to the inverse of the original matrix that you already knew, minus the inverse of A, x, y transpose, inverse of A, 1 plus y transpose, inverse of AX. Okay, so it's a formula. And you see that you don't need to compute any additional inverses. These are just matrix vector products that you need to compute there. This inverse you already knew. So to compute the inverse of the updated matrix, you don't need to compute a new inverse. You just need to apply this formula, which are just matrix multiplications. Okay? So it's effective, because if you had to compute this inverse brute force directly, again, it would take an amount of operations which would scale like n cubed, if n is the size of the matrix. Instead, here you are multiplying vectors and matrices, so computing this takes order n squared. So you see, by applying Sherman-Morrison, you go from a complexity which is n cubed to n squared. So you have a big computational gain. Okay. Okay, so let's apply this formula again to the resolvent. Okay, we are going to study the resolvent to get all the answers. Okay. So we write down the resolvent matrix associated with the data in the spike-Wigner model. So we have Z identity minus D, and D is equal to H plus tau UU transpose. So this is the resolvent associated with it, okay, by definition. So let's look at what happens if we take the inverse. So here you see we are in the framework of Sherman-Morrison because we have a full rank matrix. This is a full rank matrix plus a rank 1 matrix. So we can apply what I just wrote there, and it will give exactly this, right? Because A here is Z minus H, is the full rank matrix. And if you invert Z minus H, this is just the resolvent of H only. Okay, so we have the first term there. Here we have minus, here we have a plus, so this minus becomes a plus, plus tau, and this, okay, x and y for us are just UU transpose, so this term is exactly this, right? A inverse again is the G of H here, UU transpose G of H, 1 minus, because again I have to change of sign, U transpose GHU. Okay, so it's a direct application of Sherman-Morrison. Okay, so now we want to study where is the location of a possible outlier eigenvalue for the data. Okay, now by outlier I mean an eigenvalue which will be at a location beyond the end point of the semicircle law. Okay, it means that it goes beyond the eigenvalues of the noise. Okay, so you see that how can we detect the location of an eigenvalue from the resolvent of a matrix? Remember, for a generic matrix M, the resolvent so the resolvent is well defined for everywhere in the complex plane for Z. The only locations that you have to avoid are the locations of the eigenvalues of M, right? Because if you set Z to an eigenvalue of M, I remember that this, if you do the spectral decomposition, is written like this. You see that there will be a term here that will explode if Z takes a value equal to one of the lambda i's. So this Stieltjes transform is not well defined only at the locations of the eigenvalues of M, because you get divergences. Okay? So it means that if you are away from eigenvalues of this matrix, this is a well-defined analytic function. There is no poles, no problem. And at location of eigenvalues, you have poles. Okay? Perfect. So you see, by definition, now we are focusing on a z, which will belong to the real axis, because we want to detect the presence of an eigenvalue. So it's a real number, because we're working with symmetric matrices, which is beyond, which is strictly after the endpoint of the semicircle. So let's look at a z which is strictly greater than 2. Okay? For a z strictly greater than 2, and we want this resolvent to explode at this location. It means that d has an eigenvalue at this location, at this outlier. Okay? This divergence cannot come from this term. This is the resolvent of the noise only, and when the eigenvalues of this matrix H are bounded between -2 and 2. Okay? So the only possible source of divergence comes from this term. But again, the numerator is well defined for z greater than 2, because the numerator here is only is an analytic function of z, because it's just products of these resolvents. Okay? So the only possibility for observing a divergence is that this denominator goes to 0, so that this term explodes. Okay? So this gives us an equation for the location of the outlier. We can simply look at a z strictly greater than 2, so beyond the GOE, the semicircle, such that this denominator explodes. Okay? So this is what I'm saying. We're looking for a solution to this equation. We want this denominator to be 0, which will lead a divergence in the resolvent matrix of the data. And therefore, it indicates the presence of an eigenvalue, which by construction is not in -2 and 2. So it's an outlier. Okay? So we just solve this equation. That's very simple. Because again, we use the same trick, that if you sandwich, you see here we have a quadratic form. We have U transpose a matrix G, U. And this U is a vector which is independent of this matrix H, and therefore this matrix G. Okay? By independence, you can show that when n is large, in the large system limit, such a quadratic form always tends to the trace of the matrix. Okay? So as before, 1 over n the trace, because this vector has a unit norm, so you get a 1 over n. So again, the 1 over n trace of this matrix is, when n is large, precisely the Stieltjes transform, okay, by definition of the Stieltjes transform. So what we obtain is, we are looking for a z beyond 2, so we call it lambda 1, the top eigenvalue, such that this equation is verified, and we know that this term here is essentially the Stieltjes transform of the semicircle law. So we have this equation. Okay? And that's it. You solve it, and this gives the critical value. This gives the location of the outlier eigenvalue. Okay? And if you solve it, you realize that this equation has a solution only, so a solution outside the semicircle, so greater than 2, only if the SNR is greater than 1. Otherwise, there is no solution outside of the bulk. It means there is no outlier. Okay? So we just we have done two things. We have found the location of the outlier eigenvalue, which is given by this equation, and this you can solve it, and it gives what was in the result. So it gives this thing. This is a very simple equation. It's a quadratic equation to solve. So we have the location of the outlier eigenvalue, and we also have the condition under which this outlier exists, which is this condition. So we have the BBP transition, the critical value of the signal-to-noise ratio. So we solved the first part of the result, location of outlier and critical value of the SNR. Is there a question? Okay, I will assume not. If there's one, just stop me. Okay. So you see, I mean, it's very simple, the analysis. It's surprisingly simple. Of course, then you may wonder why does it have a name, and why did we discover this until just in 2000? These kind of things were known, but to make them rigorous, you have to work a bit more. Here, it's what I'm showing to you is not fully rigorous. You have to be slightly more careful, but yes, it's surprisingly simple. The true proof, the complete proof, is what I'm saying, but you have to fill in all the epsilons, of course. Okay, let me finish then the proof of the BVP result. So now we have shown this. So using Sherman-Morrison, we have shown that if tau is less than 1, we do not observe an outlier. And if tau is greater than 1, there is an outlier, so an eigenvalue beyond 2, and we also got the location of this eigenvalue. Okay? Now let's first maybe show you that I'm not lying, and then maybe I will show you this result. So maybe I can show simulation. Yeah. Yes. If there is a question, that's a good time also while I'm opening. Okay, let me share for a moment my screen. Do you see my screen right now?
Yes, sir, it's visible.
Okay. All right. So let's start just with the simple. So just want to show to you that I'm not lying, and so you can try also. You see these are one-line codes. It's very simple. So the first thing is to show you that the semicircle distribution is really there. So I'm going to draw a random matrix X, which will have Gaussian entries with 0 mean and variance 1 over n. This is what's written there is the standard deviation. Okay. And then I'm adding X to its transpose and divide by square root 2. When I do that, you should check that what I'm constructing is precisely a GOE. You see, because when I'm summing X, so this matrix X here is non-symmetric, the one I generate first here. And they all have variance 1 over n. So when I symmetrize it by adding X transpose, you see that I'm adding Xij plus Xji, which are two independent Gaussians. And so when I sum independent Gaussians, the mean remains 0. I'm summing the means. And I'm summing the variances. Okay, so the variance of the off-diagonal elements of this matrix is 2, but then I divide by square root 2. When I divide by square root 2, I'm dividing the variance by 2. So now this is a symmetric matrix where the off-diagonal elements have a variance 1 over n. Instead, for the diagonal entries, I'm just summing twice the same element there. So I'm multiplying the variance by 4, which I then divide by 2. And so I obtain a variance equal to 2 on the diagonal. So this matrix here, once I symmetrize it here, it's precisely a GOE as defined in the lecture notes. And then I will diagonalize it. So I look at the eigenvalues of this matrix and I show you the histogram, really all the eigenvalues. And I will put on top the semicircle law to see if it fits well, and I will do that for multiple sizes. So n will go from 10 to 1000, and we'll see how good is the theoretical prediction. So each time you see a different figure, it's just that I'm resampling a new GOE matrix, and so that's why you see fluctuations, because each time the code is running is getting a new matrix for a given size n, and you see what happens. So the semicircle law is in blue there, and so you see that if you plot many matrices, you see fluctuations from one to the other. So it's because the size is small, and therefore the asymptotic theory is not very precise. So you see the locations of the eigenvalues. But as soon as I increase n, now n is maybe 100, you see right away very quick convergence of the empirical histogram to the semicircle law. Okay? And you see that it is very unlikely you see sometime an eigenvalue that slightly escapes 2 or minus 2, but it does not happen often, and it really doesn't go far, even if the size is very small. It's just 100 there. Let me increase more the size. Now I go towards 1000. You see now that the description is essentially perfect, and you will almost never see an eigenvalue escaping the bulk and the semicircle law. So you see random matrix theories. So first you have very quick convergence to asymptotic results, and it works. It's very precise. Okay, perfect. You can do the same for V-sharp matrices. So V-sharp matrices again is an empirical covariance. So I'm generating X. So here I can show you two things. First, let me generate really a V-sharp matrix defined as in the course. So X is a Gaussian matrix where the elements have zero mean variance 1 of size n by t. Okay, and then I'm constructing this empirical covariance X times X transpose, and I divide by t. And again, I do the same. I plot the histogram of eigenvalues, and I do that for different aspect ratio. You remember Q was controlling the ratio between the 2 dimensions of X. And let me change n, and you see as soon as n is 10 here, we see 10 eigenvalues, but if I make 10 even equal to less than 100, we see already an almost perfect match with the asymptotic law, which is this blue curve here. And if I change Q, so the aspect ratio of my matrix X, of which I compute the covariance, we see that the empirical spectrum changes and the asymptotic description remains very precise. Okay, and of course, if I increase more the size of the matrix X, the match is even better. Okay, so you see what you can do is that if you have a true data matrix, you can, let's say, you can compute its covariance, and you can put on top the V-sharp distribution, and if you see something else, you can already know that your matrix is not pure noise. Okay, let me show you another thing. I want to illustrate this notion of universality that I mentioned at the beginning of the course. Let me now not take any more X to be made of Gaussian entries, but of something else which has the same mean and variance. For example, we can take X to be made of plus and minus ones. So now it is a much more structured matrix, but still the matrix elements are independent, and this is the important point. But the mean, now they are Rademacher variables. Their mean is still 0, the variance is still 1, but that now every value of X can take just one of two values, plus and minus 1. And I do the same. I compute the covariance of this matrix and plot the histogram of eigenvalues. And you see that the Marchenko-Pastor description still works. This is what universality means in random matrix theory. The details of the matrix in question do not matter. You have kind of universality classes, okay? You have, it doesn't really, even if you do the theory studying Gaussian matrices because it's convenient, the final result apply to much broader class of matrices. Okay, as long as you have enough independence between the matrix elements, the semicircle distribution will work for symmetric matrix with Gaussian entries. With independent entries or weakly dependent entries, and V-chart will work for their covariance, even if the entries are not truly Gaussian. They can be something else. As soon as they're sufficiently independent and therefore can be thought as noise, because if you just draw an array within weakly dependent entries, it's basically rubbish. There are no interesting structure to exploit. Independence means no structure. Then it will be described in a universal manner by the V-chart distribution for the covariance, or by the semicircle for the matrix itself. Okay, so this is what I mean by universality. Let me now not take any more plus and minus 1 entries for X, just to show that it's robust. Now the entries of X will be real numbers between minus square root 3 and square root 3. This is the uniform distribution on an interval, and the interval is chosen such that the mean is 0 and the variance is again 1. Okay, and I can do the same. And it again works. So you have strong universality. Okay, the details do not matter. And that's why you can apply these tools to understand complex nuclei, complex objects in quantum mechanics, because the details do not matter. As at the moment where you have enough independence and complexity in the sense of large size, this kind of random matrix theory predictions will apply. Okay? Is there a question there, or? I can show you now the BBP transition. So I do the same. I will generate an X GOE matrix, exactly the same as before, that I call now the noise. So X is a non-symmetric Gaussian matrix with the correct mean and variance. I symmetrize it, and I construct my GOE matrix. Now I generate an arbitrary vector of unit norm. In this case, I don't force the norm to be strictly 1, but if you generate a Gaussian vector with 0 mean and variance 1 over n, it is very much concentrated. The norm is very close to 1 anyway. You don't need to enforce it. So I draw a U, which I will call the information, but here I draw it Gaussian, but I can draw it in any arbitrary way. It will not change. You can even take the components of this vector to be 1 and then all zeros, and you would observe the same as what I'm going to show. Then I construct my data as noise plus a signal-to-noise ratio that I call A here, times the tensor product of U with itself. So this is my rank 1 matrix, U transpose. Okay? And then I do the same. I will plot the histogram of eigenvalues of the data now of Y, and compare this to the semicircle law and to the BBP predictions. So let's do this. Oops. Okay, so here n, the size is 10. and this cursor here controls the signal-to-noise ratio. So let's increase the size. You see already I'm not even at 100, and already we see a nice semicircle. And in red, I'm emphasizing the maximum eigenvalue, the empirical maximum eigenvalue. So the one for the true matrix. No, sorry. In red, it's the location predicted by the BBP result, the one we derived. It's A plus 1 over A in this notation. Okay? So it is the location of, in theory, where should be the maximum eigenvalue of the data if the size is large enough. And now I increase the signal-to-noise ratio, and you see that indeed, until A is equal to 1, the BPP theory predicts that the maximum eigenvalue should remain at 2. And this is what we see. Okay? But beyond a critical value of A equal to 1, here I'm scanning A from 0 to 3. So here I'm still below 1, and at some point, A is large enough, and we see indeed an eigenvalue, a single eigenvalue that escape the bulk of eigenvalues. And by the bulk, I mean those related to the noise here. And you see that the theoretical prediction in red is rather accurate, even if the size is small. Here the size is maybe 20 or 30. Let me increase the size, and you see now, of course, that the precision increases. So you see this very nice theoretical prediction that matches very well what you observe. Okay, you see this single eigenvalue there predicted by the theory. So if you take real data and you plot it and you observe something of this sort, where you see a big blob of eigenvalues which are well described by some prediction from random matrix theory, you can say that these components and the associated eigenvectors are related to rubbish, to pure noise. Well, if you see something extracting like this, escaping, it probably means that it is related to information, and maybe you should take a look at the eigenvector associated with that eigenvalue. Okay, it's probably meaningful to look at it. Is there a question or? Okay, and you can also plot the eigenvector overlap. So here I've done the experiments where I've generated my data in the spike Wigner model, and then I looked at the top, the eigenvector associated with the top eigenvalue, and I computed the inner product squared with the U, the true vector we are looking for. The BBP theory told us that this overlap when n goes to infinity should be 1 minus 1 over the SNR squared, and this is this yellow curve. It's the theoretical prediction, and the blue curve is the empirical prediction. So it's not perfect because here the size is small, but if I take the size a bit bigger, it will match even better this curve, and quickly, when n increases, you will quickly see a very good match with this yellow curve. So you see this phase transition really in the same sense as in statistical physics. You see that you have an order parameter, something that a statistic we are interested in studying. Here it's the overlap of the spectral PCA estimator, the top eigenvector of the data, with the unknown vector. It is strictly 0 when the size is big, before a certain phase transition point, which is the BBP transition, and then it becomes non-zero. So you have a non-analytic behavior, 0 and then non-zero. Okay. In this case, the transition is said to be continuous in the sense that this order parameter changes continuously from 0 to non-zero. But you can have scenario where you have a jump, a discontinuity. It's called a first order transition. Well, this is called a second order transition. Okay, is there okay, we'll stop asking this because I don't get so many questions, but of course if you have any, you just stop. Perfect, so we have 10 minutes left, so I will employ them to show to you how to obtain this yellow curve. So the theoretical prediction for the spectral PCA performance. I have a
बच्चों की कम पड़ रही है टीचर्स को देने के बाद
ठीक
I request everyone to please switch off your mic.
I've done it. Okay. Sharing. If someone wants this code, it's in Mathematica. Of course, I can share it, but you can code it in 2 minutes in Python, of course. Okay. Okay, so let's prove the eigenvector overlap result. So the second part of the VBP result, and then that will be the last thing we're going to do in random matrix theory. So we want to show this. Okay. So the derivation will again be based on the analysis of the resolvent, because this is the resolvent. It contains all the useful information about the random matrix ensemble, and it's easier to manipulate than directly working with the matrix. Okay. So let's see. Eigenvector of overlap, performance of spectral PC. So let's write down the spectral decomposition of the resolvent of the data, G of D. It's a sum over all its eigenvectors, vi transpose, of its eigenvalue times its eigenvalues, z minus lambda I. Okay, and remember these vi's are the same eigenvectors as the data itself, because the resolvent is just a shift of a matrix by a diagonal matrix, and then you take an operation which is an inverse, and the inverse applies at the level of eigenvalues. When you apply a function to a matrix, in the matrix sense, it's a function that is applied to the eigenvalues, but it leaves the eigenvectors invariant. Okay. If you apply a function to a matrix, where M can be decomposed as O diagonal matrix that I will call tau, omega, which are the eigenvectors O transpose, f of M is O f of omega O transpose, where this is the diagonal matrix with f of 1, 1, f of n, n. Okay? So the inverse, of course, only applies on the eigenvalues. So these are the eigenvectors of the data. This is our spectral decomposition of the resolvent. Perfect. So until now, we have used the resolvent only to get access to spectral properties, things related to the spectrum. Okay, but the resolvent also contains the eigenvector to extract things about eigenvectors, and indeed this is the case. Notice the following thing: the quantity we are looking for, this squared overlap, is directly equal to the limit when z, the argument of the resolvent, tends to the associated eigenvalue, to the eigenvalue associated to the vector of to the eigenvectors of interest, of z minus lambda 1 times u transpose g du. It's very simple to see. I'm taking u transpose g du, so it's like if I'm putting my vectors there. This is my eigenvector overlap. The numerator is precisely 1 transpose u squared. So we see that this object is there when I sandwich my resolvent by the unknown mu. But now this thing, we have all the eigenvectors overlaps that appear. sorry, so here it's a VI. We have all these overlaps between U and VI that appear in this sum. So somehow we just need to pick one term in this sum, the one that we are interested, which is this one, okay? While these quantities, instead mixing all these eigenvector overlaps squared with those weights, okay? So they are mixed. Somehow we need just to pick one term in the sum. And to do so, you simply need to multiply by the denominator here associated with the eigenvector that you wish to extract and take z going to lambda 1. Why does it work? Because you see that so this z minus lambda 1, for every term here in the sum which is not I equal 1, when z will tend to lambda 1, this term will tend to a constant, which will be the difference between lambda 1 and another eigenvalue lambda I. And therefore, 1 over a constant times this, which tends to 0, will be 0. So we are cancelling all the terms that we want not to consider in this sum. Instead, for the term we are interested, we get a z minus lambda 1, which tends to 0. So we have a divergence in this sum. The term we want to extract is exploding. And then we tame down this explosion by remultiplying by this quantity that tends to 0 at the same speed. So we are just picking the term of interest in the sum. Okay? So it's direct. Okay? And then the next trick is to use again the Sherman-Morrison formula. So you write down the resolvent in terms of the resolvent of the data in terms of the one of the GOE noise plus this term, like for the derivation of the outlier location, and you use this formula. Okay. So you multiply by z minus 1 and you sandwich, you take the quadratic form with u. And what it gives, you see, if you take the quadratic form with u of that term, again, by independence of u and g, and u is a vector of unit norm, this tends to the associated Stieltjes transform. And here h is alone, so this is the Stieltjes transform of the semicircle. So here we get the same, we get a u there, transpose, and a u here, so we get the semicircle Stieltjes transform, and we get it here as well. And at the denominator, it also appears. So when n is large, we get tau, the Stieltjes transform squared, over 1 minus tau, the Stieltjes transform. Okay? So this is direct. And now you need to take the limit of this quantity times z minus lambda 1 when z tends to lambda 1. So this thing here is analytic at lambda 1 because lambda 1 is beyond the semicircle support. So here there is no issue. So this times this really tends to 0, so this term vanishes. The non-trivial term is this times this, because precisely when z tends to lambda 1, the outlier eigenvalue, we have proven just before that this equation is verified. This equation is precisely the equation that gives us the position of lambda 1. It's the equation that characterized lambda 1 when we derived its location by Sherman-Morrison. So basically this thing tends to 1. This equation is telling us that this tends to 1 when z tends to lambda 1. So this denominator is exploding. You remember this is precisely the mechanism we used to locate the outlier. So this thing is exploding. This thing is tending to 0, so that all this explodes. But this 0 is cancelled by this 0. Basically, we have the limit of we have a 0 over a 0. how do we treat limits of 0 over 0 using L'Hopital rule? Okay, so you consider instead the limit of the derivative over the derivative. Okay, so using this L'Hopital rule, you take the derivative of this object over this, and what you obtain is this. You do it, and this by using the form of the semicircle Stieltjes transform, you obtain directly 1 minus 1 over tau squared. Okay, so very simple derivation again. All this once you have understood that many things can be solved with the resolvent, it's just a matter of understanding the first step, how to extract the quantity you want from the resolvent. And in this case, it was very simple because this identity is direct. Okay. The non-trivial thing is then to realize that you should re-express this resolvent in terms of Sherman-Moison, in terms of extracting the component due to the noise, the resolvent of the noise. And then you solve and you get the eigenvector overlap. So we have now characterized the performance of the simplest possible algorithm you can think of, which simply takes the data, look at the top eigenvector associated with the largest eigenvalue, and calls this the estimator of U. Okay, so this is PCA. This is the simplest PCA, principal component analysis. Okay, but this is a suboptimal algorithm because this algorithm does not exploit any prior knowledge you may have about this unknown vector, this rank 1 matrix. Instead, if there is something to exploit, you should do it through the Bayesian approach, and you get better performance, and you remember this picture. So this is a bit of a mess, but what we describe now is the performance of this algorithm. Here is the BVP transition there, and the performance becomes non-trivial there. But there exists a better algorithm, a Bayesian algorithm, whose performance is here. So am I back? Okay. I was just concluding. I was saying that the analysis of this Bayesian algorithm gives a better performance than PCA. There will be done towards the end of the course. Discuss it a bit, but we have done something very important. We have described a threshold phenomenon, a phase in the very important signal extraction problem. And this is this BBP transition for principal component analysis. Okay. Okay, so I hope the course was clear. And is there any question that you may have?
Do we have any questions?
Okay, so if there's not, we'll meet again later.
Okay, the next, I thank Dr. Jan Barbier to please for the kind words and showing the importance of different transitions and matrices theory, also with examples. So I hope it was a fruitful session for all of us. And I am really learning and gaining a lot of things, sir, myself also. Thank you.
Good, thank you. See you later.
Yes, so we now will be joining back after 2 hours at 2:30 p.m. as per Indian time. Okay, sir. Thank you.
Goodbye.
Okay, bye.